We're going to move into talking about discrete random variables and some probability distributions. And if you have a textbook or you're following along, you'll find that this spans a couple of different chapters in the book. There's a few things in probability in the book that we don't cover. And then chapter 5 is the discrete random variables chapter, so they're not together. So just keep that in mind. To start us out, though, we'll talk about probability theory, and it helps us to extend concepts that apply to variables of finite populations. So things like relative frequency distributions and the mean and the standard deviation to other types of variables. So in doing so, we're led to a new notion, and this is the discrete random variable. So we're going to talk about the fundamentals of discrete random variables. We're going to talk about the probability distributions and some of the concepts around the mean and standard deviation of the discrete random variable. Okay, so let's define the random variable. And a random variable is a quantitative variable whose value depends on chance. And you learned before when we were talking about descriptive statistics that a variable is a characteristic that can vary from one member of a population to another. And so when one or more members are selected at random, then the variable becomes a random variable. So if you think about it, random variables come about naturally as quantitative variables of finite populations, especially when we're thinking about it in the context of being random. So we have to keep in mind that there are random variables that are not quantitative variables of finite populations in the context of randomness. And I've got some examples here. For example, the sum of the dice when a pair of dice are rolled, the number of puppies in a litter, for example, like that's just discrete, and battery life in days. And you've already learned about what a discrete variable is, which is something that is usually possible to be counted or listed. And of course, that leads us into our next definition, which is a discrete random variable. And this is a variable that is countable. That is a countable number of distinct values. The official kind of definition for it states that a discrete random variable is a random variable whose possible values can be listed. In particular, a random variable with only a finite number of possible values is a discrete random variable. So again, just simplifying it, a discrete random variable usually involves a count of something. And so an example of that is the number of siblings that each student has will vary. If a student is then selected at random, the number of siblings of that student is called a random variable because it depends on chance. And we have some random variable notation, which is a useful shorthand where we'll have an uppercase X denote the random variable, or you can use any uppercase letter that you would like to use. And so, for instance, we could use X to denote the number of siblings of a randomly selected student. And then we can represent, say, the event that the selected student has two siblings by x equals 2. So you can read that as x equals 2, even though it is in these parentheses. And finally, we've got p x equals 2. And we read that as the probability that x equals 2. And again, this is just a nice little shorthand that we can use for discussing and analyzing our random variables. And this leads us to some new definitions. But what you'll see is that over on the left-hand side, I also have the definition for relative frequency distributions and histograms. The reason I am bringing this up is because we talk about distributions and people tend to not understand what that means. A distribution itself gives all the possible values of the variable And then you can add on to it. So if it's a relative frequency distribution, it will give you all the possible values of the variable and the proportion of times each value occurs. Now, with a probability distribution, it's a listing of all the possible values and the corresponding probabilities of a discrete random variable, or a formula for the probabilities. And of course, the histogram is just then the graph of that probability distribution. So what this means is that the probability distribution and the probability histogram of a discrete random variable show its possible values and their likelihood. Distributions in general will show you all of the possible values and their frequency. So when we move further in, we'll start to talk about things like our t-distribution, our chi-square distribution. They are all just a listing of all the possible values and their likelihood, and then they might be elevated with some information like a probability. All right, let's look at an example of where we would look at a probability distribution of a discrete random variable. So let X denote the number of siblings from a randomly selected student. So 0 siblings, 1, 2, 3, and 4. The frequency at which it's occurring over the total, which is 40, will give you your probability. Now remember, we are going to denote this as P X equals X, where the smaller x could refer to any of the numbers you may be looking for. So if you're looking for example, 2, how many have 2 siblings, then you would have P, the probability of X is equal to 2. So here it's asking us to determine the probability distribution of the random variable X, Px equals X. And that's what we're doing here. By going through and finding the frequency of this occurring, you're also getting the probability of that discrete random variable. Now, one of the facts, and it's a key fact that will help you through this, is that the sum of the probabilities of the possible values of a discrete random variable will always equal 1. So it's a good way to check your work to see if you've done it right. Now, we want to obtain the probability of each of the possible values, and then it's asking us to obtain Px equals 2. So it's asking us to find the probability a randomly selected student will have 2 siblings. And here we can just apply the F over N rule, where the probability of X equaling 2 is equal to the frequency over the total, which is equal to 11 over 40, or 0.275. And the second part of this question would be to construct a probability histogram for the random variable X. And of course, the histogram is just a quick and easy way to visualize how the probabilities are distributed. And most of the siblings have one other sibling. So to construct a probability histogram for X, we would plot its possible values on the horizontal axis and display the corresponding probabilities on the vertical. So referring to the table, we would end up with this probability histogram of the random variable X. So to take it all back, why are we doing this? It's because this data is discrete. I often do this to myself where I tell you the fun fact before the slide. So fun fact, a variable's probability histogram is identical to the relative frequency histogram apart from the labeling, so they'll look the same. And also the probabilities will always sum to 1, which is a really great way for you to check your work before proceeding and then having to go back and redo a whole bunch of things. So for any discrete random variable X, we have the sum of the probability that X equals X is equal to 1, or the sum of the probability of a discrete random variable is equal to 1. And we'll do an example. Let Y denote the grade level of a randomly selected elementary school student. Then Y is a discrete random variable whose possible values are 0 through 8. Use random variable notation to represent the event that the selected student is in 5th grade. So hopefully you pause the video or you're thinking about what you would write here, and you will find that Y, because we're letting Y denote the grade level, is equal to 5. Now it says determine the probability that Y equals 5 and express it in terms of percentages. So we can utilize the F over N rule here, and we will have P, or the probability that Y equals 5, is equal to 3,633, which, if you're like, oh, wait, where did you get that from? Those are the grade 5 students, divided by the total of 30,300 or 30,000, 33,000. Wow, it's been a long day. 33,999. And so we can see that 0.10, or about 10% of the elementary school kids, are in 5th grade. And finally, in part C, it's saying determine the probability distribution of Y. And so the probability distribution of Y is obtained by computing every single probability of Y equals Y. So we would do it for grade 0, I guess, kindergarten through grade 8 here. We already have Y equals 5 in here, so we just do it for the other numbers in here. All of these numbers are your distribution. And of course, it needs to equal 1. And so let's interpret the probability distribution. In many independent observations of a random variable x, the proportion of times each possible value occurs will approximate the probability distribution of x. So it's just saying that all of the frequencies, or all of the numbers that you get, if you plot that, that's what your probability distribution is going to look like. And equivalently, the proportion histogram will approximate the probability histogram for x. So it means all possible outcomes together account for 100% of what can happen here. And this here is a simulation for, throwing a coin in the air and seeing how many heads and tails you get. What's important here, though, and what I'm really trying to get across, is that if you look at these two visuals, they look extremely similar. They're just a little bit different from each other. And that's what we would expect. One of them is the proportion, and one of them is the probability. And so, as expected, proportions are fairly close to true probabilities, and this is a result that we can see really easily when we compare over a histogram. So key fact 5.2, the interpretation of a probability distribution. In a large number of independent observations of a random variable x, the proportion of times each possible values occurs will approximate the probability distribution of x, or equivalently, the proportion histogram will approximate the probability histogram. So it's just saying the proportions that you get will approximate the probabilities. There might be a little error around it, but it's pretty good. In this final section, we're going to talk about the mean and the standard deviation of the discrete random variable. And what I hope you take away from it and what you see is that the mean and the standard deviation of the discrete random variable are analogous to the population mean and the population standard deviation. Just a reminder, the population mean mu is equal to the sum of x over capital N, and this is the language we can use to extend to the concept of discrete variables. The mean of the discrete random variable x is denoted by mu sub x, or where no confusion arises, just simply mu. So hopefully you guys are cool with just going forward with just mu. And it is defined by this formula here, which states mu is equal to the sum of x multiplied by the probability of x equals x. And so that means that to obtain the mean of the discrete random variable, multiply each possible value by its probability and then add those products together. The terms expected value or expectation are commonly used here in place of the term mean as well. So let's do an example. consider a population of 8 students whose ages and years are given in the table I'm showing here. Let X denote the age of a randomly selected student, and using the table, express the mean age of the students in terms of the probability distribution. All right, so what are we going to do here first? The first thing that we want to do is we want to calculate mu. This will always help us with moving forward, and it's one of the things that I'm going to start telling you guys to do right out of the gates. Anytime you're getting a question that has a whole bunch of data in it, or even just this small amount of 8 students, always calculate the mean first, because you're likely going to need it somewhere else along the way. So calculate your mean, and you can do that by summing up all of these variables here. So 19 plus 20 and all of that divided by 8, which is the total. Now, the next thing that we want to do is we want to show that we can express the mean of the variable of this population in terms of a probability distribution. And because we know that mu is equal to the sum of x multiplied by p x equals x, then right away the most meaningful thing that we can do is start to write out exactly what we need, right? So the sum of x times p x equals 19 plus 20 times p x equals 20, and so on from there. So this expression is meaningful for a discrete random variable, but there is a kind of a better way to show this and then calculate it. So let's do that. In the last example, we talked about how to do it, but now we're actually going to do it. So an example here, a bank has 6 tellers and they're available to serve customers. The number of tellers busy with customers at 1 p.m. varies by day to day and depends on chance. Past records do indicate that the probability distribution of X is as shown in this table. And then it's asking us to find the mean of the random variable X. All right, so the first thing we need to do is we need to pull up our equation for the mean of a discrete random variable. So here it is. It is equal to mu equal to the sum of x multiplied by p x equals x. Okay, so how do we get this actual answer of 4.118? So what we need to do is we need to multiply each of our x's, so our distributions, by to their px equals x, and then sum it all up. So 0 multiplied by 0.029 is equal to 0. 1 times 0.049 is equal to 0.049. 2 times 0.078 is equal to 0.156, and so on. Now, just to back it up a little bit, you will be given these numbers for a question like this, so you don't have to find these anywhere else, but you will have to calculate these ones here. Once you sum all of these up here, you get 4.118. And if you look at it, it is the sum of this equation here. And so the mean number of tellers busy with customers is 4.118. So let's interpret the mean of a discrete random variable. In a large number of independent observations of a random variable x, the average value of those observations will approximately equal the mean mu of x. And the larger the number of observations, the closer that average tends to be to the mu. So this means that the mean of a random variable can be considered the long run average value of the random variable in repeated independent observations. And this is very important when we're thinking about experimentation. Now, I find that a lot of students find this section very confusing. And at the very minimum, if you're confused about the interpretations and all the wording, the two things you need to take away from this is the formula for calculating the mean of a discrete random variable and the standard deviation of a discrete random variable, which we'll talk about next. So we'll extend it a little bit further with the standard deviation calculation. So you may see a formula, and then you will see a computing formula as well. The formula that you should be using is the one that I am showing on here. This is the computing formula, and it is sigma is equal to the square root of the sum of x squared times px equals x minus mu2. And it says the standard deviation of a random variable x indicates how far on average an observed value of x is from the mean. The smaller the number, the closer it is to the mean. And that holds true for all standard deviations. But let's get back up to this kind of scary looking calculation. We're going to put it into play with an example and break it all down. And honestly, it's not scary at all. So we're gonna do the same example with the bank tellers that we had previously used, and we're just gonna kind of build on it. So we've got our x variables. We have our px equals x here, okay? Now let's go back to this equation here. They're asking for the sum of x squared times px equals x. Well, we didn't do that last time. So the first thing we have to do is we have to take all of our x's and we need to square them. And yes, you have to do it individually for every single one. Otherwise, it will not work. You can't just take the answer in the end and square it. It doesn't work that way. So let's start with that. Let's start by taking the sum of our x squared. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on from there. Now, the next step is to multiply it by our px equals x, which again, this was given to us, and then we'll sum the bottom of that, and that will give us this whole section up in here, okay? So let's look at that. So x squared times px equals x, and what I've done here is I would take 0, and I multiplied it by 0.029. And then I took 1 and I multiplied it by 0.049. And then I took 4. I multiplied that by 0.078 and I got 0.312. Then I took 9, I multiplied it by 0.155 and I got 1.395 and so on. The sum of that, then you can just pop right into the equation and it's all of this right here. And it's subtract mu2. Well, mu is just the mean. We already calculated the mean. And so often what you'll find with these example questions is that you'll do the mean and the standard deviation together. So you build on the whole thing. So we already calculated the mean and all we have to do is square it. So we just have to take 19,438, subtract 4.118 squared, and then take the square root of everything. And you will find that the standard deviation here is 1.6. So roughly speaking, on average, the number of busy tellers is 1.6 from the mean of 4.118 busy tellers. So again, what we need to do now is just a ton of practice, and your lab is going to help you with that this week. Now, I have on here Excel example. I can show you guys how to do this very quickly on Excel if you want. Just let me know if you're utilizing Excel or if you're preferring your calculator.